Hello everyone, my name is Sakar Chetri. Today I'll be presenting a literature review on the ethics of human-robot collaboration in manufacturing. This is for NTRE 6750, Ethics in Robotics. In this review, I examine the research on the ethical challenges that occurs when human and robots work together sharing a workspace. First, I will provide technical backgrounds on collaborative robots, then discuss major findings from the existing research, analyze the topic by explaining the ethical theories including Aristotle, virtue ethics, Kant's duty ethics, and utilitarianism, and finally discuss the application and remaining research gap for this topic. Why does this matter? For decades, industrial robots were working separately from people. They operated behind safety fences because they were designed for speed, power, and repetitive tasks, and not for working alongside humans. In those environments, the ethical questions were relatively straightforward because people and robots rarely share the same workspace. Today's collaborative robots have changed that relationship. Instead of working behind the fence, they work directly alongside people, assisting them with heavy, repetitive, and dangerous tasks. This matters because robots are no longer just machines performing isolated tasks. They are becoming teammates and influence how people work, make decisions, and stay safe. As the human and robots are shared the same workspace, questions about safety, trust, privacy, accountability, worker autonomy will become just as important as productivity. As robots become more and more integrated into the workspace, we must consider not only what the robot can do, but also how they should be designed and used responsibly. The key question is how can robots improve human work while protecting safety, dignity, and autonomy? A cobalt or collaborative robot is an industrial robot built to work safely right next to people. It combines the traditional robotic automation with technologies that allows safe interaction with humans. Unlike older industrial robots that operated behind protective barriers, Cobalt use sensors and safety systems to detect human presence and avoid impactful collision. It also uses machine vision and AI to help with the task as well as look at its surroundings. They are commonly used for tasks such as assembly, quality inspection, packaging, and material handling. One of the main advantages of cobots is that they can perform physically demanding tasks, while humans can focus on high-level tasks such as decision-making, creativity, and problem-solving. However, because humans and robots share the same workspace, ethical concerns become more important. Research are not only asking whether the robot work effectively, but also whether they have been designed and implemented responsibly. This literature review, the research paper were compared using four common criteria rather than simply summarized. The first criteria was safety, since protecting workers is one of the primary goals of collaborative robots. The second focused on human interaction and trust, examining how researcher believes human and robots can work together effectively. The third evaluated the ethical issues discussed in each study, including accountability, privacy, transparency, and human autonomy. Finally, the paper were compared based on the contribution to the broader vision of human-centered manufacturing, where technology is designed to support and empower people rather than replace them. Across the literature, there was broad agreement on collaborative robots that they improve safety and productivity. However, there were less agreement on the issues of trust and accountability, revealing an important ethical gap that motivated the remainder of the presentation. The first major theme identified across the literature is safety and productivity. Researchers agree that collaborative robots provide significant benefits when they are designed and implemented correctly. Vivani and colleagues examined human-robot collaboration in an industry setting and showed that cobots can reduce repetitive and physically demanding tasks while improving ergonomics. Similarly, Jatari and colleagues emphasized that successful collaboration depends on proper robot design, programming, and safe interaction with human and machines. There is an ISO standard 10218 that provides industrial safety framework for collaborative robots, including requirements related to force limitation, collision detection, and safe operation. More recent research expand the definition of safety beyond just preventing physical injuries to people. Gutierrez and colleagues identified safety, ergonomics, and human factors as a major research area for collaborative robotics. Lasota and colleagues further emphasize that worker safety also includes psychological factors such as stress, comfort when interacting close to robots. Overall, the literature strongly agrees that cobots can improve workplace safety and productivity. However, the research also emphasizes that robots should support human worker rather than replace human judgment. The goal of collaborative robot is not to remove humans from the process, but to create a safer and more efficient human-robot teamwork. The second major theme identified in the literature is human trust and worker well-being. For collaborative robots to be successful, workers must trust that the robot will behave safely, reliably, and predictably. Across the literature, researchers agree that trust depends on the factors such as reliability, transparency, and communication. Hancock and colleagues conducted a meta-analysis examining the factors that influence trust in human-robot interaction. The research found that robots' own performance and reliability are among the strongest factors affecting how much people trust robotic systems. However, the research also identified an important challenge: determining the appropriate level of trust. If the worker do not trust the robot enough, they may avoid using the technology. On the other hand, if they trust it too much, that can create problems as well. Workers may assume that the robot is always correct and fail to recognize unsafe conditions. A simple comparison is GPS navigation. Most people trust GPS to provide direction, but they still use their own judgment when the system provides incorrect information. Collaborative robot requires the same balance. The goal is not complete dependence on robot, but calibrated trust, where workers rely on the system while maintaining human oversight and decision making. The third major theme identified in the literature is accountability and ethical governance. As cobots become more intelligent and autonomous, determining the responsibility becomes increasingly difficult. For example, imagine a cobalt misidentifies a situation and causes a worker injury. Who should be held responsible? Is it the worker operating the cobalt, the engineer who designed it, the software developer who wrote the control algorithm, the manufacturer, or the company that deployed the system? Researchers generally agree that responsibility cannot simply be assigned to the robot because robots are tools. They do not possess moral agencies or legal responsibilities. This challenge was described by Andreas as the responsibility gap. He argued that when autonomous systems learn or behave in ways that are not fully predictable, it becomes difficult to identify a single individual who should be held morally responsible for the outcome. Floridian calls approach the issue in a different perspective. Rather than focusing on who is to blame after something goes wrong, they propose an ethic principle such as accountability, transparency, and fairness to guide how AI systems should be designed, governed, and used. Together, these researchers agree that accountability is essential, but they differ on how responsibility should be assigned. As a result, there is still no universally accepted legal or ethical framework for determining responsibility when collaborative robots make decisions that contribute to harmful outcomes. This remains one of the most significant gaps in robot ethics. The table summarizes how each sources contribute to overall discussion of collaborative robots and ethics. It compares what each one adds to the field and where its limitations are. Vivani and colleague provide one of the most comprehensive technical reviews of the cobots, making it an excellent foundation for understanding how cobots are designed and used safely. However, their focus is primarily on engineering rather than ethical decision making. Zatari and colleagues build on the work by examining human-cobalt interaction and trust, while Longo and colleagues shift the discussion toward Industry 5.0 by emphasizing human-central technology and ethical design. The ISO standard provides the practical safety requirements that many manufacturers follow, but it focuses on technical compliance rather than a broader ethical questions. The remaining sources expand the discussion beyond engineering. Gutierrez and colleagues provide a systematic review of system and ergonomics, while Losado and colleagues argue that safety should also include protecting workers from psychological stress, not just preventing physical collisions. Hancock and colleagues contribute quantitative evidence explaining how trust developed between humans and robots, while Matthews introduced the concept of a responsibility gap, highlighting the challenge of assigning accountability as robots become more autonomous. Finally, Floridian calls broaden the discussion by proposing ethical principles such as accountability, transparency, and fairness that can guide responsible development and deployment of AI systems. Taken together, these sources show how understanding collaborative robots require both technical research, which explain how the robot works safely, and ethical research, which explain how they should be designed, governed, and used responsibly. After reviewing the literature, several important patterns become clear. First, there is a strong agreement that collaborative robots improve workplace safety, reduce physically demanding tasks, and increase productivity when they are designed and implemented responsibly. Across nearly every source, researchers emphasize that cobots should support human workers rather than replace them. Second, while the technology has advanced significantly, the difficult questions are no longer about building better robots. They are about how people and organizations use them. The literature consistently identified accountability, workers' privacy, job security, and long-term trust as major ethical challenges collaborative robots faces. Finally, researchers agree that there are several important gaps remain. Future work should focus on developing explainable AI so the workers understand why robots are making decisions, conducting long-term studies on human-robot collaboration, and establishing ethical governance framework that clearly define responsibility. While many studies focus either on technical performance of collaborative robots or ethical principles, this review brings those perspectives together by connecting the literature with virtue ethics, deontology, and utilitarianism. It provides a more complex framework for evaluating how collaborative robots should be designed and developed in manufacturing. Overall, this review shows that the future of collaborative robots is not simply a technical challenge, it is equally an ethical challenge. Success will depend on designing a system that improves safety and productivity while keeping humans at the center of decision making. The first ethical theory we'll discuss is Aristotle's virtue ethics. Unlike ethical theories that focus primarily on rules or consequences, virtue ethics focuses on character. The central question is not simply what action we should take, but rather what kind of engineer, company, or organization should we be. Aristotle believed that good decisions come from developing virtues such as responsibility, honesty, fairness, and practical wisdom. The ultimate goal is human flourishing, meaning helping people live safer, healthier, and more fulfilling lives. Applied to collaborative robots, virtue ethics suggests that engineering should design robots that do more than just improve efficiency. They should create systems that genuinely improve workers' well-being by reducing dangerous or repetitive tasks, while still respecting human skills and judgment. This connects directly to the literature review. Many of the researchers emphasize that cobots should support human workers rather than replace them, which closely reflects Aristotle's idea of promoting human flourishing. The second ethical framework is Kant's duty ethics, also known as deontology. Unlike virtue ethics, which asks what kind of person or organization we should be, Kant's theory asks what's the right thing to do, regardless of the outcome. Kant believed that the ethical decision should be based on moral duties and respect for people. His important principle is that people should always be treated as ends in themselves, never merely as a means to achieve another goal. Applied to collaborative robots, this means that the companies have the duty to protect worker safety, privacy, and autonomy. Decisions about the automation should not be based solely on improving productivity or reducing cost. Instead, organizations must consider how those decisions affect the people working alongside the technology. This connects directly with the literature review. Researchers consistently identify privacy, accountability, and human oversight as major ethical challenges. From a Kantian perspective, these issues matter because they involve respecting workers as individuals with rights and dignity, not simply as a part of production process. The manufacturing advancements also supported this idea by emphasizing human-centered manufacturing, where technology is designed to serve people rather than replace them. Third theory is utilitarianism. Unlike virtue ethics, which focuses on characters, or Kant's duty ethics that focuses on moral duties, utilitarianism evaluates based on the consequences. The central question is what decision creates the greatest overall good while minimizing harm. Applied to cobalts, a utilitarian would weigh the benefits and the potential harm of using cobalts. The literature identifies several benefits, including reducing workplace injuries, improving productivity, increasing product quality, and allowing workers to focus on high value tasks. However, the literature also recognized potential harms, such as job displacement, worker privacy concern, and increased stress if employees become overly dependent on automation or feel like they are constantly monitored. From a utilitarian perspective, a cobalt are ethically justified when the overall benefits to the worker, companies, and the society clearly outweigh the negative impact. This connects directly to the literature review. Nearly every study highlighted improvements in safety and productivity, while also identifying ethical concern about stuff like privacy, accountability, and workers' well-being. Utilitarianism provides a framework for balancing those competing outcomes and determining whether technology produces more good than harm. The research identified several recurring themes, and each ethical theory helps us evaluate those themes from a different perspective. For example, improving worker safety and productivity align closely with utilitarianism because those outcomes increase the overall well-being and reduce harm. At the same time, virtue ethics also support worker safety because a responsible engineer should design systems that promote human flourishing. Issues such as privacy, autonomy, and human dignity are better understood through Kant's duty ethic. From a Kantian perspective, workers should always be treated as individuals with rights and dignity, not simply as a means to increase production. Finally, the Industry 5.0 emphasized responsible engineering and human-centered manufacturing, which closely reflects to Aristotle's virtue ethics by encouraging organizations to develop technologies to support people rather than replace them. The key takeaway is there is no single ethical theory that fully addresses every issue in collaborative robots. Together, virtue ethics, duty ethics, and utilitarianism provide a more complex framework for evaluating how cobots should be designed and used responsibly. Rather than competing with one another, these ethical theories complement each other by examining collaborative robots from different perspectives, character, duty, and consequences. To see how this ethical theory apply in practice, consider a company introducing collaborative robots to increase production. From the perspective of Aristotle's virtue ethics, the question is whether the company is acting responsibly and promoting human flourishing. A virtuous organization should use cobots to improve worker safety, reduce repetitive tasks, and support employees rather than simply increasing profits. From a Kant's duty ethics, the focus shifts to moral responsibility. Workers should always be treated as people with dignity and autonomy, never merely as a means to improve productivity. Company has a duty to protect worker safety, respect privacy, and involve employees in decisions about new technology. Finally, utilitarianism asks whether introducing collaborative robot creates the greater overall good. This means weighing benefits such as fewer workplace injuries, higher productivity, and improved quality against potential harm like job displacement, privacy concern, and increased workplace stress. This example demonstrates why multiple ethical theories are valuable. Each theory examines the same decision from a different perspective. Virtue ethics asks whether the company is acting responsibly. Kantian ethics asks whether the workers are being treated with dignity and respect. And utilitarianism asks whether the overall benefits outweigh the harm. Rather than relying on a single ethical theory, all these three provides a more complete and balanced framework for evaluating how collaborating robots should be designed and deployed responsibly. Although the current research has provided valuable insight into collaborative robotics, several important questions remain unanswered. First, most of the evaluation collaborative robots over a relatively short period of time. Further research has examined how trust, teamwork, and collaboration evolve as people work alongside the robots over months or even years. Research also needs to be better understanding the long-term impact on workers, including stress, job satisfaction, and acceptance of the collaborative robotics in the workplace. Another important area is explainable AI. Workers should be able to understand why the robot makes particular decision, especially when that decision affects safety or production. Finally, ethical governance should continue to evolve alongside the technology as collaborative robots become more capable and autonomous. Regulation and accountability frameworks will be needed to ensure that these systems remain safe, transparent, and human-centered. Overall, the literature suggests that the future of collaborative robots is not only about developing smarter robots, it is about developing more responsible ways to integrate them into workplace. The next challenge in collaborative robot is not simply building a better robot, it's to build a better relationship between humans and robots. In conclusion, collaborative robots represent an important advancement in modern manufacturing. The literature shows that the cobots can improve workplace safety, increase productivity, and reduce physically demanding work when they are designed and implemented responsibly. However, this review also demonstrates that technical performance alone does not determine whether the collaborative robots are ethical. Issues such as trust, accountability, privacy, and human dignity are just as important as efficiency and productivity. By applying Aristotle's virtue ethics, Kant's duty ethics, and utilitarianism, we can see that each theory provides a different perspective on the same technology. Together, they offer a more complete framework for evaluating how collaborative robots should be designed, deployed, and governed. Ultimately, the future of manufacturing industry should focus on collaboration between human and robots, where technology enhances human capability while respecting human dignity, autonomy, and well-being. In other words, collaborative robots should not be judged solely by what they can do, but by how responsibly they were designed, deployed, and integrated into the workplace. Thank you for your time.